The boost converter consists of the exact same components as the buck converter. It has an inductor, it has a capacitor, it has a switch, typically a MOSFET, and it has a diode. And again, we model the load as a resistance. At the input, we have a DC voltage source. This time, the components are arranged in a different way. The inductor is in series with the input. And as we will later see, that means that the required DC current through an inductor is equivalent to the input current of the converter because they are physically connected like that. In the boost converter, the so-called switching node can either be floating or be pulled down by the MOSFET all the way to ground when the MOSFET is turned on. In that case, the diode up here is in reverse bias because the left side is pulled to ground. And when we afterwards open the MOSFET, the inductor current forces the diode to conduct and charge the capacitor. Let's have a look at the operating modes. When the switch is turned on, the right-hand side of the inductor is forced to ground through an ideally perfect short circuit from the switch, and the current can return back to the source through the ground wire. During this moment, the inductor is getting magnetized. As the switching node here is pulled down to ground, the diode is in reverse bias and is a cut of the circuit. Therefore, it's the capacitor's responsibility to supply the load with its necessary charges to generate the output current, which we can see up here. Now, the equivalent circuit diagram, taking the open into account, is just simply an open here, and drawing the short circuit in a way that the inductor is getting pulled to ground, we can put the inductor in parallel with the input voltage source. The right-hand side of the diagram is hardwired and nothing is changed by the state of the switches there. The capacitor is in parallel with the load resistance. During the off time of the switch is getting an open and the inductor current is forcing the diode to conduct all its current. Remember, the current in an inductor cannot jump, and charge the voltage across the capacitor, as well as supplying the necessary charges to create the output current, which then is the same voltage as the capacitor voltage across the load, and the return path for the current to the DC source is through the ground. As the diode transfers into a perfect short circuit, the inductor forms a second-order low-pass filter together with the capacitor and the resistor. Again, the right-hand side of the diagram is hardwired, and now the inductor feeds its current into the parallel circuit of capacitor and resistor. Applying the same averaging method as we did in the buck converter, we need to derive the inductor voltage during both states and the capacitor current while the switch is turned on and while the switch is turned off. During the on time of the switch, the inductor is in parallel with the input voltage source. That means the input voltage is applied across the inductor. During the off time of the switch, Kirchhoff's voltage loop is applied by having the input voltage on the left-hand side of the inductor and the capacitor voltage on the right-hand side of the inductor. That means VL, the voltage across the inductor, is the input voltage minus the capacitor voltage. For the capacitor current, Kirchhoff's current law becomes handy. And here the output current is flowing the opposite direction as we have defined the positive symbols across the capacitor. That means the capacitor
current
minus I out. And during the off state of the switch, we have the inductor current flowing into the positive node of the capacitor, the output current flowing out of that node, while the capacitor current is also flowing out of that node. Now, again, writing all the currents flowing outside of the node on one side of the equation and all the currents flowing into this node on the other side of the equation. And at the end, solving for the capacitor current, we got the inductor current minus the output current as the capacitor current during the time when the switch is off. Now, taking the next step of the averaging method and weighting the voltage across the inductor during the on time with its valid period, which is D times the period of the operation of the converter, and weighting the voltage across the inductor, here Vin minus Vc, with the valid period during which the switch is off in the operation of the converter, that is 1 minus d times the whole period, and equaling this to 0, we can simplify that equation and rewrite it as Vin is equal to 1 minus d times the capacitor voltage. Doing the same thing for the capacitor current, we weight the output current, the minus the output current, with the duty cycle times the operating period, and 1 minus duty cycle times the operating period is getting weighted with the capacitor current during the off time of the switch. When we rewrite this equation, the negative output current equals minus 1 minus the duty cycle times the inductor current. Rewriting both of those equations into the ratio of the capacitor voltage, which is the output voltage, divided by the input voltage, gives us 1 over 1 minus the duty cycle. And we get the same equation for the ratio of the inductor current divided by the output current. Now, graphically deriving the right-hand side of the equation, we can start with the hyperbola 1 over d. Adding a minus in front of that mirrors the whole function from the first quadrant into the second quadrant. And finally, offsetting the dependent parameter, here d, with the factor of 1, moves the whole plot with a factor of 1 to the right-hand side. That gives us a few operating points that are rather interesting for a boost converter. At a duty cycle of 0%, the equation 1 over 1 minus d equals to 1. That means that the output voltage is equal to the input voltage. And from there on, it only can rise with the rising duty cycle. At a duty cycle of 0.5, we get an output voltage being twice as high as the input voltage. And theoretically, at a duty cycle of 1, that means of 100%, the output voltage would rise towards infinity. Now, this is valid for an ideal boost converter only. Practically, this transfer function describes the operation of a boost converter up to a duty cycle of around 0.7 pretty well. After the 70% duty cycle, so up here in this area, the assumptions we made are rather limiting. First of all, with the rising output voltage, we get a rising output current, and that means we also get voltage drops across the series resistance of the inductor in the circuit, as well as voltage drops during the conducting diode. So that would limit the amount of output voltage that we actually could get out of a boost converter. And that limit practically looks around like that in this graph. Furthermore, we assume that the voltages of the capacitors are steady, so DC, and the currents through the inductors are DC as well. Now, if we are approaching the state where the duty cycle is 100%, that means the inductor is getting magnetized all the time and has no time at all anymore to deliver its charges to the capacitor. Would mean that the diode would be blocking all the time, and eventually the output capacitor would discharge all the way down to zero and not being able to deliver any energy to the load anymore. For most of the investigations on boost converters in this course, we therefore try to stay outside the red operating area as it is drawn in this diagram. By making a further assumption again that the converter is 100% efficient, we can rewrite the ratio of the input current to the output current as the inverse of the current transfer functions. That means they are equal to the output voltage divided by the input voltage. And the output voltage divided by the input voltage is the DC transfer ratio of the boost converter in its valid operating range, 1 over 1 minus D. Taking the ratio of the inductor current divided by the output current into account from the last slide, which also is 1 over 1 minus D, and solving that one for the variable b I out, we can put the right-hand side of the lower equation into the current transfer functions and replace I out with 1 minus D times the inductor current. And this confirms our assumptions that we made when we had our first look at the circuit diagram, that the input current is actually equals to the inductor current. Now, if we again relax the requirements we made when applying the averaging approach, here during the on time of the transistor, we can again put the equations that we derived from Kirchhoff's voltage law across the inductor inside Ohm's law, and we see that the inductor current is actually a function of time, a first order function of time with an offset. And using Kirchhoff's current law for the inductor current, we have the negative output current flowing through the capacitor during the on state of the transistor. Note, compared to the buck converter, the capacitor current is independent of the inductor current here because the diode is blocking the two from each other. That means that the capacitor voltage during the on state of the switch also is only a first order function of time with an offset. During the off time of the transistor, so from the duty cycle until the period time, we have the input voltage on one side of the inductor and the capacitor voltage on the other side. Furthermore, we have the DC offset current from the on state of the switch. This again gives a first order function of time for the inductor current. Now, noting already that we know that the input voltage would always be lower or equal to the output voltage, we can see that this function is going to have a falling derivative. Kirchhoff's current law for the capacitor current in the second state, the state when the diode is conducting and the switch is off. Remember, we are ending up with a second order low pass filter, having an inductor in series with the parallel connection of a capacitor and a resistor. Therefore, the capacitor current is actually dependent on both the inductor current and the resistor current, which is the load current, and we end up having about the same integration as we had in the buck converter, and ending up in a double integral over time, which eventually leads to a parabolic function, a term which is the first order of time and an offset. When plotting the capacitor voltage here in green, we can start out by plotting the DC transfer function of the boost converter, which is 1 over 1 minus the duty cycle, and we arrive at the level, which is the offset, the average, the DC value of the capacitor. During the on state of the switch, we had the negative output current flowing through the capacitor, which is giving the derivative through Ohm's law on the capacitor voltage here. During the off state of the switch, we ended up in a parabolica with the simplifying assumptions that we made. So that's a second order term of time and a first order term of time represented by this equation. The inductor current is also 1 over 1 minus the duty cycle times the output current, which gives us the DC level for the inductor current. The so-called ripple is centered around that from its lowest value to its highest, often also referred to the peak-to-peak current. The derivatives of this current can be derived from Ohm's law across the inductor. During the switch conducting, we have the input voltage divided by the inductance, whereas at the off state of the switch, that is when the diode is conducting, we have the input voltage on the left-hand side of the inductor, and through Kirchhoff's voltage law, we subtract the voltage from the capacitor, which is on the right-hand side of the inductor, and again, we divide it by the inductance. This is called the dIdt of the inductor current, and all of these variables can come very handy to calculate various operating conditions for a boost converter. Note again that this analysis is valid for inductor currents being bigger or equals than 0. This mode is called the continuous conduction mode, or also called CCM, equivalent to what we've seen from the buck converter. Also equivalent to the operating modes of a buck converter, a boost converter can operate in this so-called continuous conduction mode, here abbreviated as the CCM, or in the boundary conduction mode, which I abbreviate here as BCM. Sometimes you would also see this one being called the critical conduction mode, and therefore also being very rarely abbreviated as CCM, which can be confusing with the continuous conduction mode over here. Boundary conduction mode means that the inductor current is starting exactly at 0 and reaches exactly the value 0 again at the period time t. Furthermore, there is the discontinuous conduction mode, or DCM mode, which means that the inductor current reaches the 0 level before the period is over and stays approximately 0 for the rest of the period. Now, the mathematical analysis that we have just conducted on the boost converter is not valid in this mode anymore, but we will very soon in this course have a look at what's going on in a boost converter and also in a buck converter in discontinuous conduction mode.